As the world shifts from fossil fuels to renewable energy, more and more companies are entering the space to develop the next generation of electricity storage technology to maximize the power sourced by renewables.
A 150-year-old battery design, dismissed as obsolete, ignored by scientists, and left to rot in textbooks until now. Because in the chaos of today's energy crisis, this relic has roared back to life. It's cleaner, lasts longer, and could rewrite the future of power itself. There's a type of battery that was almost left behind in history.
So the other two batteries are principally lead-acid batteries and lithium-ion batteries. The worldwide market for that is about $90 billion, and they at the moment are roughly 50-50, so about $45 billion each.
It's not one of the headline-making technologies you hear about today, like lithium-ion or solid-state. In fact, for decades, it sat in old patents, mostly forgotten by engineers working on more fashionable solutions. It didn't cause explosions. It wasn't a breakthrough that suddenly appeared out of nowhere, and it certainly wasn't new, but it also never truly disappeared. And now, as the world looks for safer, more affordable, and more sustainable ways to store energy, it is being reconsidered. This is the zinc-bromine battery, a chemistry first developed in the late 1800s. It was never intended for use in smartphones, laptops, or electric sports cars. Instead, it might be better suited for something far more important: storing energy for the grid. That means balancing solar and wind power, providing backup electricity to communities, and operating in places where safety is more important than squeezing the most energy into the smallest space. The idea of going back to a 19th century invention may sound counterintuitive in a century driven by constant innovation, but the zinc-bromine battery offers a few qualities that make it worth a second look. It's inherently safer than many modern alternatives because it uses a water-based electrolyte that doesn't catch fire. It's relatively simple to manufacture, especially if you already have the equipment for older battery types like lead-acid. And it can last for thousands of cycles without significant degradation, which makes it attractive for long-term stationary applications. This raises a natural question: if zinc-bromine batteries have been around for so long, why didn't they take off decades ago? The answer lies partly in the timing of technological priorities and partly in the limitations of the design. For much of the 20th century, the global push in battery research and manufacturing was focused on high energy density. In other words, packing more power into smaller, lighter devices. That's essential for things like portable electronics, electric vehicles, and aerospace. Zinc-bromine batteries were never competitive in that race, because their structure and chemistry tend to make them larger and heavier. They weren't ideal for a mobile phone or a laptop, let alone a car. Lithium-ion technology, on the other hand, emerged in the late 20th century and offered exactly what engineers and consumers wanted at the time. It was lighter, more compact, and capable of delivering high power in short bursts. Once it began to mature in the 1990s and early 2000s, lithium-ion batteries quickly became the default choice for most portable applications. Manufacturers scaled up production, costs dropped, and lithium-ion designs improved year after year. As a result, many alternative battery chemistries, including zinc-bromine, were left behind. They simply didn't have a clear commercial niche in a world chasing lighter and smaller. While researchers occasionally revisited the technology, there was little incentive for companies to invest heavily in something that didn't fit the fast-growing portable market. However, the energy landscape has changed. Over the past 2 decades, renewable power sources like solar and wind have become much more affordable and widely deployed. These technologies have one major challenge: they produce electricity when the sun is shining or the wind is blowing, not necessarily when demand is highest. To make renewable energy a consistent and reliable part of the grid, large-scale energy storage is needed. That's where the conversation shifts from small, lightweight batteries to robust, long-lasting systems that can operate safely in a wide range of environments. In this new context, some of the disadvantages that once held back zinc-bromine batteries are less relevant. Grid-scale storage systems are not concerned with fitting inside a pocket or a car chassis. They can be larger and heavier without affecting performance. What matters more is safety, lifespan, cost, and the ability to operate in demanding conditions without constant maintenance. And in those areas, zinc-bromine has strong potential. Lithium-ion batteries, despite their many advantages, are not without significant challenges when scaled up for grid use. Mining lithium is resource-intensive. Some studies estimate that extracting just 1 ton of lithium can require hundreds of thousands of gallons of water, a process that can put strain on regions already facing water scarcity. Lithium extraction also often involves environmentally sensitive areas, leading to concerns about long-term ecological damage. There's also the issue of volatility. Lithium-ion batteries can overheat, and in some cases enter a state known as thermal runaway, a chain reaction that can lead to fires or explosions. These incidents are rare relative to the number of batteries in use, but when they do happen, they can be difficult to control. Large-scale lithium battery fires have been reported in energy storage facilities, sometimes burning for days and releasing toxic smoke. In environments where safety is paramount, such risks need to be weighed carefully. The supply chain for lithium is another concern. Demand for lithium has surged with the growth of electric vehicles, consumer electronics, and renewable energy storage. This demand has pushed prices up dramatically in recent years, creating uncertainty for long-term project planning. When the price of a key raw material is volatile, it can affect not only manufacturers but also the utilities and businesses that rely on the technology. These challenges don't mean lithium-ion is unsuitable for grid storage. In fact, it's already widely used in that role. But they have prompted researchers, companies, and governments to explore alternatives that might offer complementary benefits. Zinc-bromine is one of those alternatives. One of the main reasons it is being taken seriously now is that the global battery market is diversifying. It's becoming increasingly clear that no single battery chemistry will meet all needs. Just as we use different fuels for different purposes, petrol for cars, natural gas for heating, diesel for ships, it makes sense to have multiple battery technologies tailored to specific applications. Lithium-ion might remain the best option for portable devices in electric vehicles, but zinc-bromine could serve in stationary roles where safety, cost stability, and durability are more important than compact size. Another reason for renewed interest is technological refinement. While the core chemistry of zinc-bromine hasn't changed much in over a century, engineering improvements have made the batteries more practical and cost-effective. Advances in materials, manufacturing processes, and system design have reduced some of the inefficiencies that plagued earlier models. In addition, the shift toward renewable energy has created a demand for batteries that can perform reliably in diverse environments, from hot, arid deserts to humid coastal regions. Zinc-bromine's non-flammable electrolyte and tolerance for high temperatures make it well suited to such conditions. Unlike lithium-ion systems, which may require complex and energy-intensive cooling systems to operate in extreme heat, zinc-bromine batteries can often run without active cooling, which simplifies installation and reduces operational costs. There's also an economic angle to this resurgence. Building a large lithium-ion battery manufacturing plant from scratch requires substantial capital investment, sometimes in the range of hundreds of millions of dollars. By contrast, zinc-bromine batteries can often be manufactured using modified versions of existing production lines for lead-acid batteries. That means companies can enter the market with far less upfront cost, making the technology accessible to a wider range of manufacturers, including those in developing countries. All of these factors contribute to the zinc-bromine battery's reappearance on the energy storage stage. It's not being promoted as a universal replacement for lithium-ion, and that's an important distinction. Instead, it's being positioned as part of a broader toolkit for meeting the world's growing demand for energy storage. In some scenarios, lithium-ion will remain the preferred choice. In others, zinc-bromine might offer a better balance of performance, cost, and safety. One major challenge is the extraction of lithium itself. Mining lithium is resource-heavy, often requiring vast amounts of water. In some mining regions, it can take hundreds of thousands of gallons of water to produce a single ton of lithium. This becomes a significant problem in areas already under water stress. Furthermore, lithium mining can lead to long-term environmental concerns, including habitat destruction and soil contamination. These impacts have raised questions about how sustainable the lithium supply chain will be as demand increases. The cost of lithium has also been volatile. When demand surged in recent years, particularly due to the growth in electric vehicle sales, prices rose sharply. This was felt across the battery supply chain, affecting manufacturers and consumers alike. High and unpredictable prices make it difficult for industries relying on lithium to plan long-term investments, and it creates uncertainty for utilities looking to invest in large energy storage projects. Safety is another area where lithium-ion has limitations. While most lithium-ion batteries operate without incident, when failures do occur, they can be severe. The phenomenon known as thermal runaway can cause a battery to overheat, ignite, and sometimes explode. Large-scale lithium-ion battery fires are challenging to control because they can burn for days and release toxic gases. Fire suppression is not straightforward, and in some cases, specialized approaches are required to contain the incident. For stationary storage facilities, especially those located near populated areas, this risk is a serious consideration. Despite these issues, lithium-ion technology still dominates because for many years the alternatives either cost more, offered lower performance, or were less commercially mature. That situation is now changing as energy storage needs evolve. Instead of only focusing on making batteries smaller and lighter, there is a growing emphasis on safety, lifetime cost, and performance under tough conditions. These priorities open the door to other chemistries, including zinc-bromine. Zinc-bromine batteries operate on a different principle than lithium-ion cells. They are a type of redox flow battery, which means they use liquid electrolytes stored in tanks, circulated through a central cell stack during operation. In a zinc-bromine system, one electrolyte contains zinc ions, and the other contains bromine. As these liquids pass through the cell stack, a chemical reaction occurs that releases electrons, producing electricity. Charging the battery reverses the process, redepositing zinc on one side and converting bromine back into its charged form. One advantage of this design is that power capacity and energy capacity are somewhat independent. To increase power output, you can add more cell stacks. To store more energy, you can increase the size of the electrolyte tanks. This scalability makes flow batteries, including zinc-bromine systems, well suited for applications that require flexible sizing. Flow batteries are also known for their durability. Because the reaction takes place in liquid form, rather than in solid electrodes that physically expand and contract, they tend to experience less mechanical stress. Zinc-bromine systems can be fully discharged without damage, and they avoid the flammability issues associated with lithium-ion cells. The electrolyte itself is water-based and inherently non-flammable. While these characteristics have long been recognized, early zinc-bromine systems had practical challenges. Traditional flow battery designs involve pumps, pipes, and large tanks, making them bulky and more complex to install. This was acceptable in some large fixed installations, but limited the technology's appeal in smaller or more space-constrained applications. Recent developments have addressed some of these drawbacks. One example is the approach taken by Gelion, an Australian company that has re-engineered the zinc-bromine battery into a more compact form. Instead of circulating liquid electrolytes through a network of pumps and pipes, Gelion uses a gel electrolyte that stays in place. This gel is positioned between zinc and bromine-containing plates, and the whole system is enclosed in a casing similar to that of a lead-acid battery. This approach reduces complexity by removing the need for external tanks and pumps, making installation and maintenance simpler. Because Gelion's design can be produced using equipment already used for lead-acid batteries, manufacturing costs can be kept lower. The company has said that the majority of its manufacturing steps can be carried out with existing machinery, avoiding the expense of building entirely new production lines. This could make zinc-bromine technology more accessible in regions where manufacturing infrastructure already exists, but investment capacity is limited. Another company taking a different approach is Redflow, which has stuck with the traditional liquid flow battery model. Its ZBM3 battery includes tanks, pumps, and the other hardware typically associated with flow systems. However, Redflow has focused on making these systems robust for challenging environments. Their batteries are designed to operate without active cooling in ambient temperatures up to around 45 degrees Celsius, making them suitable for remote areas and regions with hot climates. Redflow systems are often deployed in places where reliability matters more than compact size. Examples include telecommunications towers in rural areas, off-grid homes, and industrial microgrids. The batteries can be fully discharged and recharged every day without significant wear, something that many lithium-ion batteries cannot match without shortened lifespans. The company has also implemented a self-cleaning cycle, which helps prevent performance loss over time by removing unwanted zinc deposits from the electrodes. These two examples show the range of possibilities for zinc-bromine technology. Geely has prioritized simplicity and compatibility with existing manufacturing, which could help with rapid scaling in more conventional battery form factors. Redflow has doubled down on the strengths of the traditional flow battery model, targeting environments where those strengths are most valuable. In both cases, the technology is already being used in real-world applications, not just tested in laboratories. This shift in the market is being driven by a growing recognition that the battery industry will not be shaped by a single winning chemistry. Instead, different technologies will fill different niches. Lithium-ion will likely remain the leader in mobility applications and in any scenario where high energy density is essential. But for stationary storage, especially where safety, cost, and durability are top priorities, zinc-bromine is becoming a credible option. The market for large-scale energy storage is still evolving, and the requirements for systems vary widely. Some installations may prioritize high power output for short bursts, while others need to deliver steady power for many hours. Some locations require batteries to operate in extreme heat without the benefit of climate-controlled facilities, while others need systems that can handle deep discharges on a daily basis. Having a variety of battery chemistries available allows project designers to match the right technology to the job. The renewed attention to zinc-bromine batteries isn't about displacing lithium-ion, but about filling in the gaps it leaves behind. Where lithium-ion's high energy density isn't needed, other factors such as safety, lifespan, and stable pricing can take priority. For example, in rural electrification projects or remote industrial sites, the ability to operate safely without intensive cooling or expensive fire suppression systems can be a decisive factor. The electrolyte in a zinc-bromine battery is water-based and does not ignite. This eliminates the risk of thermal runaway, a chain reaction that can occur in lithium-ion cells when they are damaged or exposed to high heat. Thermal runaway can escalate quickly, releasing flammable gases and generating enough heat to ignite neighboring cells. In large lithium-ion battery installations, even a single cell failure can cascade through the entire system, leading to large-scale fires. Incidents involving large lithium-ion battery packs have made headlines in recent years. Fires at utility-scale storage facilities in Australia and the United States burned for days, releasing toxic smoke that required special handling by emergency crews. In some cases, water alone was not enough to control the fire, and crews had to wait for the battery to burn itself out. While these incidents are relatively rare compared to the number of systems in operation, they highlight the risk inherent in using a flammable electrolyte at scale. Zinc-bromine avoids this specific hazard. Even under severe abuse, such as being exposed to very high external temperatures or mechanical damage, the battery will not burst into flames. In some designs, bromine itself acts as a flame retardant, This has been demonstrated in controlled tests where zinc-bromine batteries continue to operate after exposure to heat levels that would severely damage or ignite a lithium-ion pack. Other flow battery chemistries also offer similar safety advantages, such as vanadium redox systems. However, these often come with trade-offs. For example, vanadium flow batteries use vanadium oxide dissolved in sulfuric acid. While non-flammable, this electrolyte is highly corrosive and toxic, requiring careful handling and disposal. By comparison, zinc-bromine electrolytes, while still hazardous if mishandled, are less corrosive and easier to manage. The bromine component does have a strong odor, which can act as a built-in leak detection feature, making small leaks easier to detect before they become a problem. Cost is another area where zinc-bromine batteries can have an advantage. Raw materials for zinc-bromine systems are generally cheaper than those for lithium-ion or vanadium flow batteries. Industry studies have estimated that the chemical costs for vanadium flow batteries can be more than 10 times higher than for zinc-bromine. System-level costs, which include not only the battery materials but also supporting equipment, installation and housing, can also be lower. Zinc-bromine batteries do not require expensive fire suppression systems or extensive climate control, both of which are often necessary for large lithium-ion installations. The design of some zinc-bromine systems further reduces manufacturing costs. Geelyon's approach, for example, reuses existing production lines originally built for lead-acid batteries. By doing this, the company can avoid the expense of building entirely new facilities. Estimates suggest that converting a lead-acid plant to produce zinc-bromine batteries at gigawatt-hour scale could cost a fraction of what it would take to build a new lithium-ion gigafactory from scratch. This could make the technology more accessible to smaller manufacturers and encourage production in regions that might not have the resources to invest heavily in new infrastructure. Operating costs can also be lower. Because zinc-bromine batteries can operate without active cooling in a wide range of temperatures, they avoid the ongoing energy costs associated with air conditioning in hot climates. This not only saves money, but also improves efficiency by reducing the system's own energy consumption. Performance over time is a critical consideration for any energy storage technology. In stationary applications, where batteries are cycled daily to store and release renewable energy, durability is more important than peak power output. Zinc-bromine systems can typically last for thousands of full cycles without significant degradation. Some designs are rated for more than 5,000 full charge and discharge cycles, which is often more than twice the cycle life of certain lithium-ion chemistries. This means that over their lifetime, they can store and deliver more energy per unit of initial investment, reducing the effective cost per kilowatt-hour. Round-trip efficiency, the amount of energy you can get back compared to what you put in, is another important metric. While lithium-ion batteries typically achieve efficiencies of 90 to 95% under ideal conditions, modern zinc-bromine designs can reach around 85 to 90%. While slightly lower, this level of efficiency is acceptable for many grid applications, especially when weighed against the safety and durability benefits. Temperature tolerance is an area where zinc-bromine often outperforms lithium-ion. In hot climates, lithium-ion batteries can degrade faster and require cooling systems to maintain safe operation. Zinc-bromine systems can often operate in ambient temperatures up to 45 or even 50 degrees Celsius without active cooling. This makes them particularly well suited to regions where maintaining climate control is costly or impractical. Real-world deployments show how zinc-bromine's characteristics translate into practical benefits. Systems have been installed in remote telecom sites, off-grid homes, and industrial facilities where they endure daily cycling and sometimes extreme weather conditions. Because they can be fully discharged without damage, they offer flexibility in managing energy reserves, something that can be valuable in off-grid or backup applications. Zinc-bromine batteries are not without limitations. They are heavier and bulkier than lithium-ion systems for the same amount of stored energy. This makes them unsuitable for applications where space and weight are critical, such as electric vehicles or portable electronics. They also have slower response times compared to some other battery types, which means they may not be ideal for certain high-power short-duration tasks. However, these limitations matter less in their target applications. For long-duration stationary storage, the priority is not to be as light or compact as possible, but to be safe, reliable, and affordable over many. In these contexts, zinc-bromine's disadvantages are outweighed by its strengths. As the energy storage market matures, it is becoming clear that no single technology will dominate every application. Instead, the future grid will likely use a mix of battery chemistries and other storage solutions, each chosen for its suitability to a specific role. Lithium-ion will likely remain dominant in mobility and portable devices. Zinc-bromine, along with other flow battery technologies, could play a significant role in stationary storage, especially for integrating renewable energy into the grid and providing backup power in challenging environments. The resurgence of zinc-bromine shows how changing priorities in energy storage can breathe new life into older technologies. Safety, durability, and cost-effectiveness are becoming just as important as size and weight. As renewable energy continues to expand, the demand for robust, long-duration storage solutions will grow, creating opportunities for a wider range of battery technologies. In that context, zinc-bromine batteries are no longer just an interesting historical footnote. They are an actively developed and deployed option, already proving their worth in the field. Whether they become a major player in the global energy storage market will depend on how quickly manufacturers can scale production and how well the technology competes with other emerging options. But their current trajectory suggests that they are likely to remain part of the conversation for years to come.